Hello everyone. In the last class, we started our discussion on functions, which tries to associate a set of elements to another set. We have also seen that the function is actually a subset of the relations where we only allow that each element from a domain to map uniquely with an element in the codomain. We have also defined certain kind of properties of functions, and also we introduced two new definitions of functions which we know as one-to-one or injective functions, and a set of functions which we know as onto or subjective. If you remember that the primary difference was that in one-to-one functions that each element in B should be mapped with a particular element, will be associated with a particular element from the domain set. That is, that if there should not be any element in B as shown here that can be associated with more than one elements from the set A, which is the domain. So this is not an one-to-one function. However, in onto, the only necessity is that I need every element of B to be associated from some element of A. In this case, the codomain contains an element which is not associated from anyone. So this is not one-to-one and onto. Whereas we have also seen the definition of function restricts, considering the definition of relation, that each element of the domain can be associated with a unique element from the codomain. It should not be the case that each element from the domain has two associations with two different elements in the codomain. Then I can tell this is not a function but a relation. And we have also seen that the two types of functions, that is one-to-one and onto, if some function satisfies both, then we call it as a bijective mapping or bijective function. Further, we also propose that how do we define binary operations among the set of elements. And we have seen that these binary operations we use day to day in our algebraic system, and we saw some of the properties like commutativity, associativity, etc. We have also defined something called identity and projection operators. We have defined identity function, which is basically a function which relates every element of a domain to itself. We define what are called equal functions, when every element gives rise to the same mapping or the same mapped element in the codomain. With that, in the background, we started to define what are called composite functions, which are basically compositions of more than one functions together. And we have seen that the composite function does not follow the commutativity principle in general, whereas it follows the associativity, that is, you can compose a set of functions in any order without disturbing their occurrences. Just you can bracket and compose it in any position. We have also proven that if two functions are bijective, that is, two functions are one-to-one, f and g, the composed function gof is also one-to-one. Further, we also seen that if both are onto, then the composition will also be onto. But interestingly, the reverse case, that if I found that for two functions g and f from b to c and a to b, where g compose f is a to c is one-to-one, then I can say only my f function is one-to-one. I cannot say anything about g to be one-to-one or not. And we have seen an example for that. We have also seen if I allow gof to be onto, then I can only say g to be onto. I do not have any restrictions on f whether it can be onto or not. And we have seen examples that f is not onto but g must be onto, as we have proven. So with this concept, let us try to move ahead in today's lecture and try to define what we call our inverse function. Inverse functions you have used already in your algebraic system, where you have seen that there are certain numbers which is identity, as I introduced in the previous class, that for addition operation over a set of integers, you find 0 to be the identity, because after that operation it does not change any element's value. Whereas if you consider that if an element, for which are the elements available in that particular number system or set that can give me back the identity, is the concept of inverse. So inverse says that for addition in the integer system, I say that for every element there is a minus a which we add gives me back to the identity. So with this example, we can define inverse, that inverse is a function from the opposite direction of the function that for which we are trying to compute inverse. Suppose f is a function from set a to b, I define inverse in such a way that it is a function from the reverse direction from b to a, such that if I compose it from the left side, FL inverse, which is one inverse I define, I get an identity, and that identity will be over set A because f is operated from over a to b first, and then I operate over FL inverse, which is from b to a, so I map back to again to a. And if I do the composition from the right side also, I reach an identity just like previous one. I got IB here because my domain and codomain changes in order. So we call that such function which upon composition produces the identity element is the inverse of that function. And if the composition from the left side produces that, then we call it FL inverse as the left inverse. If there exists a function which composition from the right side or the first you operate over that followed by f gives me the identity, then we tell it as a right inverse. Invertible functions are extensions over the notions or definitions of left and right inverse. We call a function f from a to b is said to be invertible if there exists a function f inverse from the reverse domain, that is from b to a, such that f inverse from the left, that is the left inverse composed with f, provides also the identity, and the same function composed from the right side as a right inverse provides the identity. Now a question to ponder, which I will address a little bit afterwards, is that I am saying that some function to be invertible if there exists one such function where the left inverse and the right inverse are the same and produces identity. So the definition, as the definition says, that the inverse operated with this is the will produce the identity is as per the inverse function's behavior. But the only thing that I have not proven yet is that the inverse should be unique. So a function is invertible if I reverse the map and get a function from where both side inverse will produce me according identities. And we call that function f inverse is as the inverse function. We have also, as we are discussing, that there could be two inverses, but actually those inverses are unique. So the uniqueness of inverse property says that every function which is invertible shall have only one inverse. And it is very straightforward to show it because you assume for the contrary there are two inverse. So if you assume that this is also an inverse and that is also an inverse, so f1 inverse and f2 inverse both will follow these two properties because f is invertible. So in case of f inverse you substitute with f1 inverse, and here also f1 inverse. In case of this you substitute with f2 inverse, and here also f2 inverse. So if you assume that 2 inverse exists, then 2 inverse will satisfy these 2 into 2 4 properties. Now see this functional compositional jugglery, that f1 inverse is nothing but f1 inverse composed with the identity, because the identity composition gives me back the same function as we have seen in the last class. So this identity is nothing but f composed with f2 as per the definition of invertible, and f2 is my inverse. Now the associativity rule provides me to bracket it anywhere. That's why I can shift due to association I can shift the bracket here. Now this is as per the invertibility definition, again provides 1a, that is the identity, and identity map composed with the function f2 inverse gives me back f2 inverse itself. So I started with f1 inverse and come back through this process and ended up with f2 inverse, all being the same. So therefore it contradicts the notion that two inverses are different. So all the inverse that I produce are all same. So therefore I have unique inverse if it exists and if the function is invertible. Let us give you an example that if two functions are from integer to integer defined as 2x and gx is defined as x plus 1 by 2 floor. So two compositions GOF and FOG both defined from the Z to Z because it's the same set from and to which we are mapping. So GOFX is basically G over Fx, which is 2x. So G over 2x means here 2x plus 1 by 2 comes. It is x plus half which we are flooring. X is integer, therefore half doesn't make any sense because we are doing a floor. So it gives back me to x. FOGX, if you see this one, it says that gx is x plus 1 by 2 floor. So f of that, basically it is x plus 1 if x is odd, otherwise it is x if x is even. Why? Because try with 5 plus 1 by 2 is 3, floor is, 5 plus 1 by 2 is 3. So f of 3 is, f is 2 into x, so 2 into 3 becomes 6. So therefore I started from 5 and got the final answer as 6. So it is x plus 1 if x is odd. If you go with 6 plus 1 by 2 is 3 by 6 plus 1 by 2 floor is 3 into 2 is 6. So if x is even just as 6, I get the answer as even 6. So this is the function that I get. Now you can see interesting observation that G from the left side composition gives me an identity function because G of x produces x itself. So G is a left inverse of f, whereas FOG does not produce me the identity. It's a different function. It is an identity if and only if x is even. If x is odd, it is not identity. So this is not identity. That means G is not the right inverse of f. So therefore, since I do not get G as left inverse producing me identity and right inverse producing me identity, so I cannot say that G is the inverse of x. So G is the left inverse definitely, but not the right inverse. The second example, which is a positive example where we show that with the same function, if you choose gx instead of this typical x plus 1 by 2 floor, but we replace it by x by 2 and make the domain as real to real, then what happens? G of fx will be g of 2x, which is x, and f of gx will be f of x by 2, which is x. So therefore, both the composite functions gives me the identity function. Therefore, GOF equal to FOG, their domain codomain matches, so I can do this function equality as per the definition, and it becomes IR. So G is the left as well as the right inverse and is the same unique inverse of f. So this is how we define and use inverse functions for a particular function. So with that definition and background, let us try to produce certain properties of invertible function. We will show that f is a function which is invertible if and only if f is bijective, that is 1 to 1 and on to. So let us try to see the if part, that is if f is invertible. So by definition, if f is invertible, then there is an unique inverse which can compose from left side as well as right side to produce an identity. We shall use that to prove that f is bijective. So this is the unique inverse. From the left side produces identity, from the right side it also produces identity. Now identity functions are nothing but just like fx equal to x. That means it just maps back the same element to the same set. So it should be 1 to 1, it should be on to. So identity functions are 1 to 1 and on to both. So considering this first criteria of the definition where IA is my injective function, so therefore this is equal to identity, so this is also an injective function, that is 1 to 1 function. Now when this is 1 to 1 function, what happens? We have just proven in the last class that then f is 1 to 1. I cannot say anything about f inverse, but f is definitely 1 to 1. Whereas when this is on to, in case of IB, if I say that IB is on to, then f is on to as well. I cannot say anything about f inverse, but this f is on to. So these two combined results gives me f is injective as well as f is surjective. So f is bijective. So we started off with assuming f to be invertible. We've proven that f is both injective and surjective. Now the opposite direction. We have to show that if F is bijective, then we can define an inverse in such a way that it will give me, composing from the left and right side, the identity function itself. So let us try to build such an inverse. So what does bijection says? Bijection says that there exists a y, for some y in set B, I have one and only one pre-image due to bijection property. Onto property says I have one pre-image, at least one. Bijection says it should be the only one, no two pre-images can be possible. So for each y, I have a pre-image of x in A. Now I try to say that I will define a new function called f inverse from B to A such that it will map every element to its pre-image. Now once I do that, then for an arbitrary y and x, what will happen? If you try to compose this function with the function f over x, so fx will give you y and f inverse y will map back to x. So this composition over x will produce back again to the same x, which means that this composition is an identity. So inverse coming from the left side composed with f is an identity. Similarly, we will show that inverse coming from the right side, so f inverse y is fx, f inverse y is x, so f composed of that is fx, which is y. So this takes y and gives me back y, so this function is also an identity. Since I can construct an f inverse or an f inverse exists such that these two compositions results as an identity, I can say that f is invertible as per my definition of invertibility. A next property, which is a little bit tricky, that if f is going from A to B, a mapping, G is a mapping from B to C, I say that these two are invertible. I assume that these two are invertible. Then I have to prove that my composition GOF from A to C is also invertible, and I have to prove that GOF inverse is this equality holds. Now let us prove one by one. Let us first try to prove this is invertible, which is pretty straightforward, right? Because f and g are invertible implies that f and g are bijective function. Why? Just proven by here, if and only if this is bijective. So if f and g are invertible, f and g are bijective. Now if f and g are bijective, their composition is also bijective. We have proven in the earlier class that if two functions are bijective, then their composition is bijective. If their composition is bijective, again we rely on the previous theorem, the backside part. If something is bijective, then it is invertible. So if it is bijective, then it is invertible. So we started from the invertibility, shown that they individually are bijective, used earlier theorem to prove that this is bijective, then used just before the theorem before to prove again back that this is invertible. This one, the second part of the proof, says that you see that I want to find that f inverse or g inverse is nothing but the inverse of this composition function. Isn't it saying that GOF inverse is equal to this? That means this part is the inverse of it. And how do we prove that something is an inverse of GO inverse? Just by composing it from the left and right side and by proving the composition to be identity. So let us do that. F inverse or G inverse composed with GOF. Associativity gives me to put the brackets anywhere. So I first do this operation. This gives me identity. Then I try to do these two operations, gives me F back. These two operations gives me 1 IA because F is invertible given. Similarly, the right side, if I try to compose this inverse is the right side, it also gives the same way. If you proceed, it also gives the identity over B. So I can see that this is the unique inverse, both sides it gives identity. So this is the inverse of composite function, hence just write it in this way. If you are convinced with that, let us take an example. So let's say fx equal to 3x plus 1, where f is defined over real to real mapping. So f is bijective, right? Because every element of its codomain has a unique pre-image in its domain, and its pre-image is just a particular element from this -1/3 is the pre-image from where it is associated with. So it's bijective definitely because it has one and only one images. You can show that injective and bijective. I kept it for you because just to show injective and bijective, you can use the concepts that has been provided in the previous lecture and can use that F is bijective and prove that F is bijective. Now, since F is bijective, F must be invertible as per the theorem, first theorem here. Then we saw that the inverse would be y minus 1 by 3 because this composed with F inverse y will give you y, and F inverse composed with Fx will give you x. You try to do that and find and see that this is the inverse. So this is what we mean by an inverse, and all of these definitions and properties, everything fall inside this kind of an example. So let us try to recap the previous lecture when we defined image and pre-images. So the direct image is, let's say F is a function from A to B, and there exists a non-empty subset of the domain. I say the image of that subset is if I take all the element association of that, all the element from the subset where it is associated with B, that is F A dash, I shall get a subset of element from the codomain, and that is my direct image. It is doing nothing but it is taking a fragment of the element from A, and it is trying to see where those elements get mapped into B. That fragment is the direct image of A dash under the function F. We define it this way. In the same vein, we can define the inverse image as well. So inverse image says that if there is a function from A to B and there is a non-empty B dash which is a subset of B, that means I am now taking a fragment from the codomain. So obviously that fragment of element must have some elements from F to be associated with. So I will take those elements from A as my inverse image of these elements. So inverse image is just the collection of pre-images of the elements of B dash, which is defined as F inverse B dash. And I say F inverse B dash is all x's such that Fx produces me the elements from B dash. So it's just an extension of the definition of image and pre-image which we defined when we started defining functions. Here is an example. Let's say Fx equal to x square from real to real, that is a function. Now I define a subset in such a way that is a real from 0 to 2 closed interval. Only those x's I take. Now the direct image of that particular subset will be all y from 0 to 4 because Fx equal to x square. So all elements that belong to the 0 to 4 area in the codomain, region in the codomain, are my direct image. The inverse image, however, if Fp would be, if you say that the inverse image of Fp, that means these elements are mapped from what elements in the set of R, the domain of R, is basically, I can see that 0 to 4 range, that this 0 to 4 range can be mapped from minus 2 to 2 ranges. So from x, if it is minus 2, I go to 4. If it is 0, I go to 0. If it is plus 2, I go to 4. So that means that it is not always the case that if you choose an arbitrary subset and take the direct image, then the set of elements you gave, now you try to come back with a reverse or inverse image, you will get the same set as the answer where you started off with. So that means that this is not a bijection. If it was a bijection, if your function f that you have chosen to be a bijection, then any arbitrary set you choose, if you go for a direct image and if you come back with that through an inverse image, it will always be same. So if there exists a set where this property does not hold, then you can claim that your f is not a bijection or invertible. Sometimes we prove the invertibility or the non-existence of an invertibility or bijection by this phenomenon also. Sometimes we do not take the whole set, rather we take a fragment of the domain and try to see what are its direct image and try to produce the inverse image from that function and try to see whether we have an equality or not. If not, it is not a bijection, and hence it is not invertible, because there is an if and only if property with bijection and invertibility. So as you can remember that in the last class we have seen that a function f a2 b, if you have a subset a1 and a2, then these properties hold. And I have proven in the last class that when this is a subset of this, in the last class it was subset equal to, but I promised you that at the next class I will show that this class, that equal to is not a valid thing always. Take this example. If f is a function from R to R, where fx equal to x square again, I choose my a1, that is from the set of real numbers, as these reals, 0, 1, half, 1/3, these are all real numbers. I choose a2 as 0, minus 1, minus half, minus 1/3, and so on. Here, my a1 intersection a2 is only the element 0, right? So f of a1 intersection a2 is f of 0, which is the element 0, because 0 square is 0. Whereas if I see that f a1 intersection f a2, what is f a1? It is 0, 1, 1 by 4, 1 by 9. What is f a2? It is 0, 1, again 1 by 4, 1 by 9, 1 by 16, and so on. So therefore this intersection is basically the same for these two sets. We get this one. So you can easily see that this is not equal to this one. And if you remember that we have shown that if f is not 1 to 1, then this holds. If f is 1 to 1, then the equality holds. Otherwise, I cannot say in general. So in this case, if you try to find out that this is, since it is a function I have taken here, which is not a bijection, therefore, the 1 to 1 definitely doesn't hold. That's why I am not getting the equality here. So that's why I try to put a recap. After the image and pre-image concept, I will revisit it and show you that the equality in general does not hold. This is a new one, depending on the pre-image concept, that A to B is an onto mapping, okay, with B1 and B2 is a subset of B. This will be a subset. It's a mistake. This notation will be a subset of B. Then, if B1 is a subset of B2, it implies that F inverse B1 is a subset of F inverse B2. It is pretty straightforward, because you take an element B belongs to B1. Since this is given to you, it automatically says B will also belong to B2. Now it's an onto mapping. So for every B in B1, there must be an element A1, A in the set A, which associates with this B in the set B1. So I can get F inverse of that B to get my A. So therefore F inverse, so my A belongs to F inverse B1. And then A also belongs to F inverse B2, which means that F inverse B1 is a subset of F inverse B2. So you see why I need an onto function here. If I do not take this onto, for this one, I cannot claim that the B that I have taken for every B belongs to B1 is a subset of B2 does imply this one. Similarly, for this one, you choose your B as belongs to this and show that your B also belongs to this, and vice versa. I try to prove the first one as just stated, and I leave the rest one to you, because it's just a straightforward thing to show the sets and subsets and equality. So if X belongs to F inverse B1, then there exists an Fx. So I need to prove if X belongs to this, then this X also belongs here. So I started off with here. So if X belongs to F inverse B1, then Fx belongs to B1. Since B1 is a subset of B2, therefore if Fx belongs to B1, then Fx must also belongs to B2. So if X belongs to F inverse B2, it implies, this implies if X belongs to F inverse B2, implying that I started off with here, I reached here, implying that this is a subset of this. So the other ones will similar, but please note here, this is equal to in general, whereas this one has a subset when we are doing a direct image, and we have seen that there are examples where it is not equal to, but this stands equal to. And while deriving this, please try to think that why this onto is very important. Here I have not done anything. I have not restricted this function to be anything. Here I have restricted this function to be must be onto. Why I need that? Just try to think on this. These are left to you as an exercise. So with that, we have learned the composition as well as inverse. Let us just come back to whatever is left over is the number of onto functions, and I told you in the previous class that it is non-trivial. Let us try to figure out that where from the non-triviality comes and can we at all count it on. First of all, tell me one thing, that if M, that is the size of set A, so I am trying to estimate the number of onto functions f from domain A to codomain B, that is how many functions from A to B are possible that are onto. So tell me that if the size of set A is M, if the size of set B is N, and if M is less than N, can we get any onto functions? Though I give you the results in red, but please think alongside with me. I shall not, because see, the number of elements in B are more, right? And now function means that an element in A cannot be associated with two different elements in B. That means that if the number of elements in B are more than A, some element of B I have to miss out. So if I miss out some element of B, then my function cannot be onto, because onto means the image of the element of A must be equal to B itself. So for every element here, I need an associated element from which I can map. So therefore, if the number of elements in A is less than the number of elements of that in B, then the onto functions are not at all possible. So therefore, to compute the onto functions at least more than 0, we should have this M greater than equal to N. Let us try to see the first basic case. It is greater than equal to, first of all, and it is greater than 0. So let us assume both are 1. So there is one element in A and there is one element in B, which is very straightforward. There could be only one mapping possible, that is directly from that element to its element, to the B element. So the number of onto mappings is also 1, and it is onto because one element I have mapped it in through A. Let us try to increase this number so that we get, if N equal to 2 and M is more than that or more than equal to that, then what happens? Forget about this magic number. Let us try to think what happens, that if let's say M is equal to 3, for 2 case will automatically come in. Let's say if M equal to 3, that means I have 3 elements in A, I have 2 elements in B. How many functions are possible as in total? So these 3 elements and these 2 elements, as per my definition of total possible functions, is the cardinality of B to the power A, which is N to the power M to the power 3. So 8 all possible functions. Among them, can you figure out which of them are not onto? See that I have also taken functions in such a way that x will map to 1, y will map to 1, z will map to 1. That is not onto, because 2 has been left out. So this is a constant function. For any value of A you give, I give you the answer as 1. I also left out this constant function similarly. So this is 2 cube or 8 is the total number of functions. 2 of them are not onto functions at all. So the total number of onto functions therefore is 2 cube minus 2 is 6. What about if I increase the value of M from 3 to M elements? The same thing happens. I have 2 to the power M number of possible functions, among which 2 functions will be such that they are not onto. Those are constant functions. So the formula is this. Now the magic formula you can relate. It is 2 to the power M minus 2. Are we done? So is it for, let's say, N and M, is it 2 to the power N minus 2? Or rather 2 to the power M minus 2 universal? So is N going to play any role here or not? Let us move a little bit. Consider there is M elements in the first, there are 3 elements in the second. Do not see the red part. This is the magic number. Try to compute first. How many total functions? Again here 3 to the power 4 if I start m equal to 4. So let me assume that I have 4 elements here, b is 3 elements, obviously 4 is greater than equal to 3, so it's no problem. I start off with it. So among these 3 to the power 4 functions, which of them will not be onto? I can left out 3 and map all of them to 1 and 2. I can left out 2 and map all of them to 1 and 3. I can left out 1 and map everything to 2 and 3. These 3 types of mapping that I just said are the categories where this is not onto. So I have to remove these sets from here. So therefore the map, so how many such functions are there? Since this is of 2 elements, 4 to 2 I have just computed, it will be 2 to the power 4 on non-onto functions, each from this and from here. So it is 3 into 2 to the power 4 non-onto functions which maps elements of A into 2 element subsets, leaving 1 element. So the running count of onto functions reduces to this much. Are we done? Not yet, because see, when you say that I will remove functions from A mapping to 1, 2, and also I will remove functions from A mapping to 1, 3. So you have also removed W1, X1, Y1 and Z1 while removing it here, because W, 1 pair, X, 1, that those constant functions are here also getting removed. So I am removing all functions from A to 1, 2. And the constant function here, W1, X1, the same constant function is also removed when I try to remove this set of functions. So I have removed the constant functions 1 twice. Similarly, if you take A2, 3 functions and A2, 3 functions, you have removed the constant functions to 3 twice. And if you take A2, 2 and A2, 3, you have removed the constant function to 2 twice. So every constant function removed twice, so we need to add it because otherwise the count will be lesser. So this kind of constant function has been removed twice. So just add those. 3 number of constant functions are possible as here. As we saw, 2 number of constant function here, similarly here 3. So we add this. Wait a minute, where we are reaching now? We are not 2 to the power m minus 2 is not a generic format. So we are reaching at a scenario where first we say that we will map everything to everything. So all possible combinations here, that is 3 chosen from this set of 3C3 and 3 into 3 to the power 4 is our combinations to map functions of length of size 4 elements to 3 elements. Among them we are removing 2 element subset domains. So how many 2 element subset domains can be made from 3 elements? 3C2. So we are removing 3C2 into 2 to the power 4 because 2 element subset domain from 4 elements gives to 2 to the power 4 functions. So we are removing 3C2 into 2 to the power 4. Then we saw that, then single element functions are removed twice. So we have to add those, and single element function from 4 elements are possible 1 to the power 4. That is only one constant function per single element is possible. And there are 3 single elements. How to choose between 3 single elements? In 3C1 ways. Now we are at a situation to somehow bound this with respect to a formula that has magically shown you in red previously. So it is 3C3 into 3 to the power m. C4 is appearing everywhere. That is our m. 3C2 into 2 to the power m. 3C1 into 1 to the power m. Wait a minute, then where we are leading for general case? You explained 2 to be this one, you explained 3 to be this one. Which should we take? So obviously this is going to be more general, where we are adding something, removing something, adding back whatever we removed multiple times. We are smelling something through these above steps, right? If we say that the number of onto functions is O, M, N from set of size M to N, what we are smelling is, this answer, the principle of inclusion and exclusion. We are including all functions, excluding the functions that are not qualified. If we excluded more, we are including it again, and this process will continue. Looking at this formula of inclusion exclusion, you can now think of, let's say, m element to n element, how many onto functions are possible. This is the magic number. To start with this number, it looks like horrible, but let me explain with whatever we have done with n equal to 3 and m. It is just n cn n to the power m, c3 c3 3 to the power n. Our n is 3 here. Then what do? We try to remove the set of functions that eliminates one element and tries to select the functions with only two subsets. So nc n minus 1, n choose n minus 1, n minus 1 to the power n. Then n choose n minus 2, n minus 2 to the power n. See this formula, this minus exclusion, inclusion, exclusion, so on up to 1 to the power n. Okay, so this is nc1, so this will be n minus 1, this comes to 1. So this is closed form, I equal to 0 to n minus 1 to the power I, n choose n minus y, n minus I to the power m. And now if you see that I can also extend it to n, because if I add if I put here n instead of n minus 1, I am just adding with 0, because n minus n cancels. So this is a better looking formula than all this jugglery. So I say that this is my onto functions. So if you are still not convinced, if you are still not convinced that your teacher might be doing some kind of a specific answers and then trying to relate it with a function, let me relate what does this mean. Combinatorial. So this is called a Stirling. There is a concept called Stirling number of second kind. So first of all, you see that number of ways to distribute m objects into n identical but numbered containers with no containers empty is just our onto function. See what we have done in onto, we have mapped m objects into n identical but numbered. 1, 2, 3, 4, 5 is our B set. For each 1, 2, 3, 4, 5, I have some m going there. So that's why number of ways I can map m objects to n identical but number container is equivalent to my number of onto functions, which is this, the closed form formula that I have just formulated. Now if you remove the assumption of numbered only n identical, then what will happen is, here if you remove this, then with no container being empty, then n factorial number of permutations here you consider due to the numbering, because 1, 2, 3, 4, 5 and mapping m will be different from if you renumber it with 2, 1, 3, 4, 5. So therefore there could be n factorial different numbering permutations possible. All of them are different onto functions. But in combinatorial definition, if we say just distribute m objects into n perfectly identical unnumbered containers, then I need to just have this 1 by n factorial going. So this number is called a Stirling number of second kind. So therefore the number of onto functions we have just seen will be n factorial into Stirling number of second kind. So n factorial comes from the fact that we are numbering the bins where we want to put our balls. Well, so this derivation, as I have shown, that which is a primer to principle of inclusion and exclusion, the Stirling function of second kind. So it's a combinatorial argument for the derivation that if m and n is positive numbers, integers, and obviously m greater than equal to n greater than 1, otherwise we have shown what will happen, it will fall down to 0, and you can see from the onto function arguments. I can compute this function recursively using these two. Now let me give you the analogy that how the Stirling function is computed. What does this mean? It means from here I have just shown m plus 1 objects to be distributed into perfectly identical n containers. What are the two different ways we can do it? One is that we can distribute m objects to n plus 1 containers, and then the remaining m plus 1th object we can put it into nth container that only will take that m plus 1th object, one object only. So it will make all the n containers non-empty, as well as it is the number of ways we can that it will contribute to this is just Sm(n minus 1), because it will be putting m objects into identical n minus 1 container, and the last object always into a last container. M plus 1th object into last container. However, if we do not allow that last container, just we say that the other option would be that I just distribute m objects into n identical containers. Now the m plus 1th object I can put anywhere in any of these n containers. So it will result me n number of ways to put this m plus 1th object itself. So it contributes that these are the number of ways to distribute m into n containers. So I can have m plus 1th thing in the first, I can have m plus 1th thing in the second, I can have m plus 1th thing in the nth container. So there are n into this many ways which can contribute me to distribute this. So we are done. Once we say that we will just leave aside m plus 1 and give it to a new container. And once we said that we will not give him a new container, we will put in some existing container. So these are the inclusion and exclusion parts of it. So the total sum will be equal to distributing m plus 1 into n identically, perfectly identical containers with no container being empty. So that's why this formula results. A little bit of jugglery in the corollary, we just multiply this with n minus 1 factorial both sides. So this will be n minus 1 factorial multiplication, just I have done 1 by n into n factorial to look it nice. This will be n minus 1 factorial multiplication, and since n minus 1 factorial into n gives me n factorial multiplication here. So this will be multiplied by n minus 1 factorial. Here it's a mistake. This will be n minus 1. So see, this is how we can do the same recursive definition over onto functions, because my onto function says that OMN is n factorial SMN. So therefore this is OM plus 1n. N remains the same, OM plus 1n. So 1 by n into OM plus 1n equal to, this is OM n minus 1 and this is OMN. So OM n minus 1 plus OMN equal to this. So number of onto functions to map m plus 1 elements into n is equal to n into these two sets. So this is what we call a Stirling number of second kind, and it's just stands upon the basic principle of inclusion and exclusion. So we have seen that how we can define functions, how we can define compositions, what are the different types of functions we have, how many of them it is possible, and in the principle of doing that we have proved certain properties of functions, binary operations, and finally we converged into finding what is called a non-trivial count of finding onto functions, and we have learned a new thing which is called Stirling number of second kind, which basically is the approximation of that number of onto functions, and this is helpful in many counting problems that you recognize. Suppose you are trying to give a password of length m from a chosen set of n different characters available in keyboard, where your password length is more than the number of characters given to you. Suppose you are given with AB and 1, 2 and you are choosing a password of length 16. So how many different passwords can you set? Same thing, number of onto functions from m to n. Suppose m cross n is a two-dimensional array of m rows and n columns, and it should be filled up with 0 and 1 values. So 0 and 1 values, why I gave you, because in algorithms and other courses you will see that such arrays are called adjacency matrix, and it is predominantly used to represent graph data structures. So it has some relation with computer science. So now you see that how many 2D arrays you can formulate or construct so that every row has at least exactly one 1 to be present, and at least one 1 to be present for every column. Okay, every row exactly one number of 1 to be present, and at least one number of 1 to be present at each column. So this is again an onto function. the same count as the onto function, you can easily formulate. You have seen problems like m different component manufacturing contracts of a high security project needs to be executed by n different companies, where I want that multiple companies work on the same component, or so no company actually is left out to operate over the m different component contracts. So how many possible ways of assignment can you formulate for these m contracts to get assigned into n companies? Answer: number of onto functions. This one looks non-trivial if you do not know whatever I discussed last 15 minutes or so. Now it is trivial because whenever m less than n, the number of onto function is 0. So this equation falls down to 0. This one is n factorial. You can easily understand this is just a variation or a mixture of onto functions with the Stirling one, which says that if your m equal to n, then it is the number of permutations that you can get. Okay. So with that, we completed a concept in algebraic structure which started off with sets, which then followed up with relationships between the set of elements. Finally, we did certain thing called the operations or functionalities, and we saw that how the counting problems and the computational problems are related to this kind of thing. So in future lectures, we will also see that how sets are used to determine the volume or the sizes, determine that what is computable, what is countable, what cannot be countable in subsequent set of lectures. Thank you.